Hello students, welcome back. So in the last lecture session we had discussed about the working of a half wave rectifier circuit. So today we shall be discussing about the full wave rectifier circuit and its operation. So as you can see here, a full wave rectifier circuit, it actually consists of two diodes, diode D1 and diode D2. So if we start understanding it from the left hand side, you can observe that there is a transformer. So at the primary of the transformer, 230 volts is being stepped down to a relatively lower voltage. Now say for example, in this case, let's assume that the step down voltage be around 24 volts. So this 24 volts, it actually gets divided into two equal halves because of this center tap. Okay, so that means plus minus plus minus 12 volts and 12 volts. Okay, so which means altogether if we consider, it will be 24 volts. So because of the center tap, the voltage gets divided into two equal halves. So let me just write it here, 12 volts plus minus 12 volts. Okay, so this is during the positive half of the input cycle. Okay, now during the negative half of the input cycle, the voltages do get changed. Okay, so let's try to understand the working of this particular center tapped full wave rectifier circuit. Let's start with the positive cycle. So during the positive half of the input cycle, now during the positive half of the input cycle, if we just observe, okay, so the diode D1 will be forward biased. Why? Because a positive voltage is being applied to the anode of the diode 1. Okay, so we can say that D1 is on. What about D2? Well, for D2, it's like negative voltage is being applied to the anode. So diode D2 is off. Okay, so what happens in this case? Only one of the diode will be on, which is diode D1. So I can just say that during the positive half cycle, diode D1 is on while D2 is off. D2 is off. So what will happen to the current? The current flows from D1 like this. Okay, so let me just indicate it. The current flows through the diode D1 and the direction of the current flow will be like this through the load resistance RL. Okay, so due to this current flow at the load resistance, I will be getting the exact replica of the input signal. Now please remember that this voltage appears only because diode D1 is conducting, whereas diode D2 will be off. Okay, so no current flows through the diode D2. The current only flows through diode D1 during the positive half cycle. Now what happens during the negative half cycle? During negative half, exactly the opposite thing happens, which means now diode D2 is off. Okay, one thing to be observed here is that during the negative half, the polarities do get changed at the secondary of the transformer. That is, during the negative half, I need to change the polarities, minus plus minus, plus. Okay, so that means during the negative half of the input cycle, for the diode D1, it's like we are applying negative voltage to the anode and enter positive voltage to the cathode, which means this will be off. D1 is off. So let me just write it here. During the negative half, D1 is off, whereas in the case of D2, we are applying a positive voltage. So diode D2 is on, whereas diode D1 is off. So let me just write D2 is on in this case during the negative half. Now what will happen to the current flow? So during the negative half, the current flows through diode D1 because it conducts. Okay, it conducts, and the direction of the current flow is as represented. Now one important observation to be done here is that during both the uh, the positive as well as negative half of the input cycles, the direction of the current flow through the load resistance is same. Okay, because during the positive half cycle the current flows in this direction, and during the negative half also the current flows in the same direction through the load resistance. Okay, so let me just indicate it. If this is during the positive cycle and this is during the negative half cycle, then the direction of the current flow is the same. Because of this reason, at the output side, the voltage appearing will not be in the negative half, whereas it will be like this. Okay, so this is an important observation that has to be done in the case of a center tapped full wave rectifier circuit. Okay, so let me just write it as D1 is I'm sorry, D2 will be on here. Okay, so it's a small correction. D2 is on while D1 is off. Okay, so D2 is on while D1 is off during the negative half cycle. Okay, so the same cycle keeps on repeating. Okay, now this is without a filter. Okay, now if you just want to note down the important performance parameters of a full wave rectifier as we had seen it in the case of a half wave rectifier circuit. Okay, so let me just call it as this is rectified output, but this is rectified output without a filter. Okay, so let us just look at the performance parameters of a full wave rectifier. Performance parameters. Okay, so the first performance parameter is V average or VDC voltage. Okay, how do we denote VDC? Well, it is the average of the output appearing across the load resistance. So if I just want to denote it as V average or VDC, this is how it can be represented. Okay, so what is the expression for VDC in a full wave rectifier center tapped circuit? Well, it is 2 Vm upon pi. For a half wave rectifier, it was just Vm upon pi. For a full wave rectifier, it is double of that. Okay, because we are getting the output in both the positive as well as negative cycles. So it is 2 Vm upon pi. Similarly, Vrms is Vm upon root 2. Okay, well, the derivations for these two expressions in the case of a half wave and also full wave rectifier circuit is explained in a separate video. The link is mentioned in the description section. Okay, so interested students can just go through those derivations. Next, ripple factor. So ripple factor for a full wave rectifier is mentioned to be around approximately 0.43. Okay, so for a half wave rectifier it was 1.21. For a full wave rectifier it is 0.43. That means overall the ripple factor is being reduced in the case of a full wave rectifier circuit. Then coming to efficiency. Efficiency of a full wave rectifier is double that of a half wave rectifier circuit, which is 81.2. Okay, so this is the idealistic efficiency of a full wave rectifier circuit. Next, coming to peak inverse voltage, this is 2 Vm. Okay, so these are some of the important performance parameters of a full wave rectifier, which we will be considering during solving of the problems or analysis of a full wave rectifier circuit. Okay, yes, so the last point to be seen here is what will be the effect of a filter circuit on a full wave rectifier. Yes, so let me just add a capacitor in parallel to the load resistance. So if I add a capacitor in parallel to the load resistance, then it acts as a filter. Now again, we have to remember that we will have to select the values of R and C in such a way that the product of R and C is large when compared to the discharging time of the capacitor. Okay, let me just mention it here. Tau, the time constant, which is product of R and C, is much larger than the discharging time of the capacitor. Discharging time of the capacitor. Okay, all right. So when we add a capacitor as a filter, what happens is, yes, so during the positive half, as it is in the case, the current flows through the load resistance, and okay, the capacitor charges to the maximum peak value of the input. So this is how we are going to get till the peak value of Vm. Okay, then what happens is the voltage at the anode as well as the cathode will be the same, due to which, okay, for a momentary amount of time, diode D1 behaves as if it is a reverse biased case, so that the capacitor charge starts discharging. Okay, so the capacitor starts discharging. Okay, now depending upon the value of the capacitance, we will be getting this particular graph. Okay, so this particular sequence goes on continuing. So again, the capacitor gets charged to the maximum peak value, and then it again discharges. Again charges and then discharges. Okay, the only difference here is that if we notice the amount of ripples, okay, well, this is the amount of ripple. With respect to the half wave rectifier, the amount of ripples are greatly reduced and the average DC content has increased. Okay, all right, so let me just clearly mention it. This is with a filter. with filter. Okay, well, I hope students have understood the operation of a full wave rectifier circuit. Thank you very much.